for the external free body diagram, I will have this point couple of 18 kip-ft. Since it's an external picture, I can simplify the distributed load. It's 2 kip per feet over 9 feet is 18 kip. It's a uniform distributed load, so it acts at the center, 4.5 feet. And where it's connected to the wall, I'm going to have the reactions from the wall. I will assume that AY is up. And arbitrarily, I said that the moment at the wall was clockwise. Like I said, I'm ignoring the horizontal force here because for right now, we're not concerned about the internal normal force, just the shear force and the moment. If I take the moment around A, I'm going to get a negative MA plus 4.5 times 18 minus 18 kip-ft. So I get 63 kip-ft, positive 63 kip-ft for the moment at A. Thinking back to when we did 211, the assumption, it's fine if it's wrong, if this came out negative, but we just have to realize that meant that our assumption was in the opposite direction it actually was. Here I happen to guess it right, so I'll leave it, it is actually in a clockwise rotation. So I need that for the next step. And when I sum forces in the y direction, I'll have negative 18 plus AY. So AY is also 18 kip, or it's positive 18 kip. This is not new. This is just EMCH 211 here, but we have to do this step first so that we can draw our VM diagram, because the top of it is going to be our loading diagram with all of the numbers we have here. So it's just, we're just going to copy this, I'll make it bigger, and put in the correct numbers and directions for these reactions. Too large for this problem. I'll make it this big. Okay, so here we do need that distributed load, 2 kips per foot. At this edge we have AY, which we know is 18 at points up. And also at A we have the internal moment, or the reaction moment, 63 kip-ft, and we know that it is clockwise. So we need the edges. So we're going to start with V, which will be in kip. Between critical lines, it's helpful to have that measurement because we need that when we're finding the integral so that we know what the length is compared to the height. So V is going to start at 0. So I'm going to establish that 0 line here first. First thing is adding any critical lines that we have, or critical points. Here, we already are marking the start of the distributed load and the end of the distributed load. There's no point loads in between. So this one will have no additional critical lines. We will see that in the next one, though. All right, so we don't have to add any extra ones. This is going to be 9 feet times 2 kips per foot. It's pointing down. The area under this distributed load will be negative 18 kip. So now our goal is, or what we do is we go from being on a line to between a line, on a line to between the line. In this case, we have one line, then we're between it, and then we're at this final line. So it's going to be fairly simple compared to when they get more complicated. All right, so what we do is we start at the extreme left, we start at 0, and we see what's happening on this line that's going to affect V. The only thing that happens on the line that affects V are point loads. At this point, there's a couple, but there's no point load here. So on the line, we're not going to change at all. We're going to stay at 0. Then we see what happens between this line and the next line. Well, we have a distributed load with an area of negative 18. So what this means is that the value of V is going to change by negative 18. We're going to, whatever we are at the left side of the line, will be negative 18 of that by the right side of the line. So by the time we get over here, we'll be at 0 minus 18, or negative 18. Then we see on this line what happens on the line. We have this point load of 18 kip. The loading, again, goes in the same direction as V, or the V goes in the same direction as the loading. We're at negative 18. We're going to change that by adding 18 kip to it, and we'll be back up to 0. So we start at 0. We're gradually going to go down to negative 18, and then immediately jump back up to 0 because of that point load. What we still have to do is, how do we go from the 0 to the negative 18? We have to connect these 2 points, and that's going to be based on the slope of the distributed load. And the same idea will be true when we go to the moment diagram. The connection is always going to be 1 degree higher as you go down on the graph. So for example, this is a straight line, or a 0th order line that has no slope, which means as we go down, this will become a first order line or a straight line. There's only one way a straight line can connect 0 to negative 18, so we don't have to worry about the curvature of it. We will have to worry about that for the M diagram, though. Again, it's a sketch. It doesn't have to be perfect, but it should illustrate the general shape that things have. Right, so this is V. It's entirely negative as we go left to right, and then it goes back up to 0. Right, once our V diagram is complete, it's helpful to, just like we did up here, start finding the areas of V between those critical points. This is a triangle. It has a base, or it has a height of negative 18, a base of 9. So the area of this triangle is negative 81. And now I'll make the M diagram a little bit easier to draw. We don't have to add any critical points because we don't have any 0 crossings in V. And the point couples are already on a line, so we don't have to add additional lines for that. So this is good. We're going to again go what's happening on the line, what's happening between the line, now for the M diagram. All right, so on the line, the M diagram is affected by point couples. Here we have an 18 kip-ft point couple that's going clockwise, which externally is negative, but internally is positive. So we will actually jump up by 18 kip-ft. Again, these reflect the change in the value of M, the change in the value of M. So we were at 0, we added 18, so we went up to 18. Then we look at what happens between the lines here. And for that, we have to look at the integral of the V diagram. Conveniently, we already calculated that this area is negative 81. So we start at 18, and by the time we get to the other line, we have to go down by 81, which means we're at 18. We subtract 81 from it. Again, this is not meant to be to scale, but we'll have 18 minus 81 will be negative 63. So by the time we get over here, we're at negative 63. And we'll see how does that change happen. We're on the line. We have another point couple here, 63 kip-ft. Again, clockwise, which is externally negative, but internally positive. We're going to change by adding 63 kip-ft. If we're at negative 63 plus 63, we jump up to 0. So we start at 0, and we're back up to 0. So we can be relatively certain that at least all of this was done correctly. We still have to fill in a couple of gaps here, but we're on the right track. Like in the V diagram, we have to see how do we connect the M diagram together. This is going to be a little bit harder because in the V diagram, we're now at a first order line. And it's good to mark that since it's sometimes tough to tell in the sketch if it's supposed to be first or second. Yeah. So externally, it's negative because it's clockwise, but it's always the opposite in the M diagram. So it's negative externally, it's positive internally. So we're adding it if it's clockwise, subtracting it if it's counterclockwise. Not to be confused with the point loads, where those are in the same direction on the V as they are on the loading. So that's the one little kind of nuance that you have to remember, that point couples go the opposite way in the M diagram. Now, so how do we connect the 18 to the negative 63? It's going to be based now on the slope of the V diagram, or I'm sorry, the value of the V diagram, because remember, the value of V is the slope of M. M, therefore, is the integral of V. So we have to use both of those ideas here. First of all, in the V diagram, this is a first order line, which means the 18 and the 63, negative 63, are then going to be connected by a second order curve, or a quadratic curve. So for a quadratic curve, though, there's two ways that we could connect this, at least in the sketch. Either it's going to be concave up, or it could be concave down, are the general curvatures we could have. So we have to decide which one is correct. And for that, we have to consider that the value of V is the slope of M. Over here, the 18, we know that the slope at 18 has to be 0 because the value of V is 0. Down here, the value of V is negative 18, so the slope of M is negative 18. Again, not to scale, really just so we have a picture of what it's going to look like. So we have a negative slope down here. We have a slope of 0 here. So the curvature, or the concavity, has to look like that. Last piece of information we're interested in zero crossings of M also, because we might want to know where is the value of the internal bending moment, 0. So how can we find where does M cross the 0? This is not to scale, and we'll see from our answer it's clearly not to scale. This is true if we're comparing, say, this leg to this leg, then the ratio of x2 to x1 is the ratio of L to 9. But if we want to compare the area of the small triangle to the area of the big triangle, what's the relationship between the legs to compare areas? Right, they're squared is the relationship for similar triangles. Solving this for L, so that will be how far we had to go to get 18 kip-ft, 18 kip-ft is going to be 4.24. Again, not to scale there, but at least we know that as we go from the left side of the beam by 4.24 feet, that's where we have a 0 crossing on the M diagram.